them to you.
Okay, guys. Yes, the mic is.
Wait a minute. Share.
Yeah.
They're incomplete. So. Okay, so now that we've reviewed S matrices, now let me talk about two very important phenomena that occur generically in any gauge theory or gravitational theory. It's the idea of soft theorems and infrared divergences. They're both very important infrared features of these theories, and later what we'll do in these lectures is that we'll use, I'm going to tell you what asymptotic symmetries are, probably not today, but tomorrow, and then I'm going to use just those symmetries to completely reproduce all of the soft stuff that I'm telling you today. So the goal of today is to just make sure that you know what are the relevant soft physics in gauge and gravity theories. Okay, so let me start with soft theorems. Okay, so a soft theorem is the following statement. It's a statement that takes the following form. So if I have an amplitude with some bunch of particles coming in, coming out, it doesn't matter. They could be anything, charged, fermions, scalars, whatever you want. And in addition to these particles, you have a bunch of other particles, which I'm going to separate out. And they don't have to be photons or gravitons in general, but they have to be massless. And the reason that they have to be massless is I'm going to now take what's called a soft limit. That is to say, it's a limit in which the energy of these particles becomes really small. And of course, because the energy is bounded below by the mass, the only way it can become really small is if the particle is massless. So there is a limit in which the energies of all of these particles becomes small. So EI goes to 0. This is called the soft limit. And it's a general feature of S matrix amplitudes. It's a really powerful property and definitely very fascinating, is that whenever I take such a limit, now there might be issues in defining this limit, like it might be important for you to tell me which of these energies are taken to be soft first. Is E1 going to 0 before E2? Or am I taking E1 and E2 to 0 simultaneously? So the answer depends on all of these details, but no matter how you take the limit, the statement is that you always factorize into a lower point amplitude and something else over here, which I'm simply going to refer to as soft factor. Now, in general, this lower point amplitude need not be the same lower point amplitude that's showing up here, like these other particles. In the example that I'm going to talk about today, namely the soft photon theorem, it is going to be that this amplitude is literally the same as that one. So I should add another. So this amplitude here is the exact same one as that with these particles removed. But generally, that does not have to be the case. So for example, for a soft photino theorem, this amplitude is essentially a SUSY transformation of that amplitude. So you have to change fermions to bosons for that to do. And even actually in the subleading soft photon case, I'm going to talk about what's called the leading soft photon theorem. I'll define all these terms soon. But there's also a subleading soft photon case, which is non-universal, and this gets corrected from higher derivative corrections. The higher derivative part of that soft factor switches the type of particles. It switches scalars to photons. So anyway, in general, this could be some other lower point amplitude, but such a factorization always exists. Now, in my opinion, that in itself is really amazing. That's already an amazing feature. But what I find even more amazing is that this soft factor in front is completely universal. It depends only on the masses and momenta and other quantum numbers of these external particles. It does not depend on the details of the interactions. It doesn't matter whether this was coming from a 5-4 theory or 5 to the 100 theory, whatever. You can write down whatever theory you want. This soft factor will always take a universal form. That's amazing. And in fact, I remember when I learned this first in QFT, this was in 2011, every time you see such universal features, it immediately suggests that there's a symmetry explanation behind it. And I remember asking this question to my QFT teacher, and he said no. And then in 2014, we published a paper proving that indeed this is derived from asymptotic symmetries, which is what I'm going to tell you in these lectures. So indeed, there is a symmetry representation, and it's the cause of all of this universal behavior that we're seeing here in this sort of soft theorem. Okay.
Do we know who this person was?
Matthew Schwartz. No, 2011. There was no asymptotic symmetries at that time. This whole celestial stuff started in 2014, so late 2013. So it was the correct answer at that time. Yeah. Okay. So what I'm going to do now for you is, in a specific example, namely what's called the leading soft photon theorem, I'm going to derive the soft theorem. And essentially the derivation that I'm going to show is basically how you derive the soft theorems in almost all other cases as well. So it's a very nice and representative thing. Another thing that is crucial is that in many cases, not always, but in many cases, especially the case that I'm going to show here today, this is not a tree-level statement. This is a non-perturbative statement about the S matrix, which of course, in hindsight, now that we know that it's coming from a symmetry, we know it has to be non-perturbative. But even before this, Weinberg in 1965 knew that this was an exact statement about scattering amplitudes. It is not like a tree level or one loop effect. So I'm going to try and provide for you a all loop orders derivation. So it's not a non-perturbative derivation, but it's an all loop orders derivation of the soft theorem. Okay. So let me start. So we'll only need two pieces of information. So what I'm going to derive for you here is the leading soft photon theorem. Indeed, since 2014, we now have many more soft theorems that are being discovered every day, basically. Because now we have this connection between soft theorems and asymptotic symmetry. So every time you discover a new asymptotic symmetry, you find a new soft theorem, and vice versa. So like we knew about the soft Photino theorem, and that can be used to derive a completely new fermionic asymptotic symmetry. And it's been a really fun exercise to learn all these new things. So this is it's not the oldest, surprisingly, but it is in our modern QFT language the earliest soft theorem that was known to Weinberg in 1965, who derived it then. Though there was, surprisingly, the subleading soft photon theorem was derived by Lowe in 1935, so before QFT was invented. So he somehow knew about the subleading soft theorem long before there was any field theory, and he just used S matrix methods to do it. Anyway, I'm going to talk about today just the leading one, and this is from Weinberg's discussion.
Is that proof of time travel?
No. But he's one of the few examples. I don't know, there's this phenomena, I forget what it's called. It's like when your name matches the physics that you do or your job. So it's like Lowe's low energy theorem was the name of that theorem, because his name was Lowe and it was a low energy theorem. Okay, so let me derive for you the soft theorem. So there's only two things we'll need. So the method I'm going to use is I'm going to use the 1 pi effective action. So the idea is that I'm going to consider the full theory, do all the UV renormalization, and then integrate out all the fields, and I'm left over with just the 1 pi effective vertices, the 1 pi effective propagators. And now all I need to do is to in order to compute any S matrix, I just need to compute tree level diagrams with these 1pi effective vertices and propagators. That's all I need to do, right? So, and I'm only going to need two facts. So here is the effective vertex, that one of the effective vertices that I'll need. Let me put in Q. So of course, in general, this is some completely arbitrary which you'll have to derive using, depends on the details of the theory, of course. But a universal feature of this thing, which is basically the renormalization condition, how do you fix the normalization of this quantity over here? The way you fix the normalization of the quantity is by saying that, oh, in the zero energy limit, it should be proportional to the electric charge that I measure in the lab, right? So there's a universal essentially a renormalization condition which tells you that gamma p mu in this limit must be, and these other factors you can fix completely by Lorentz invariance of this form 2q times p mu. Yes.
Should the momentum be p to the right?
Yes. So this is just how you renormalize the charge. So this q is the renormalized charge of the particle, of this particle that it couples to, that this photon is coupling to. P mu just fixed by Lorentz invariance. This factor of 2 is fixed by charge, this definition of the charge in terms of the matter current. It's a maybe I'll put this as an exercise. I mean, all of this other stuff you can easily derive, show that this factor of 2 should be there. By the way, this factor, so I should mention, of course, the exact factor here depends on how I'm normalizing my external states over here, which I did not mention to you before, but I'm just using the standard Lorentz invariant normalization. This is 2p0 delta, and what else do I need? 2 pi to the d plus 1. So this is the standard Lorentz invariant normalization. In fact, this 2 is coming from that 2 over here.
So it's two symmetry factor of the 3-point coupling?
No, there's no symmetry factor.
Is this some?
There's no symmetry because this is going in, that's going out. They're charged particles. Okay, so this is one piece of information that I'll need. And the other piece of information is just the propagator for the charged fields, which again in this effective 1pi theory takes the form delta p and the only property that I will need is that in the limit when this propagator goes on shell, and this is the field renormalization condition. We need this condition for the LSE theorem to be properly normalized, so that the S matrix gives us the LSE theorem, right? So on shell, when I take this limit p goes, when the limit you go p squared goes to m squared, in that case, this delta has to limit to 1. But outside of this, of course, it depends on all the details of your theory. We'll only need these two facts, just this one here and this one here. Okay, so let me now derive this off theorem for you. Any questions about these? This is a standard QFT. Okay, so I'm going to take a simple case. I'm going to start with a simple case and then I'm going to later generalize to multiple states, or perhaps you will generalize it in an exercise. I'm going to start with just this case where I have a bunch of external particles. It could be anything, and one photon. So this photon is described by some polarization tensor. So now maybe I should also say about higher dimensional photons. Remember, photons have little group. The little group for massless particles is SOD. As we just said, it's not ISOD. And photons transform in the vector representation of SOD. So they transform as in the fundamental, or the fundamental, whatever you want to call it. So the polarization tensors for the photons are labeled by a mu index, of course, because that's the space-time index. And then it's also labeled by an A index. Remember the A index that I defined in the previous lecture goes from 1 to D. So a photon has D polarizations in D plus 2 dimensions. And this depends on Q, the momentum Q of the photon. This is for a photon. And for a graviton, you have something similar. You have mu nu, but AB. So a graviton transforms under the symmetric traceless rank 2 representation. So in other words, these AB indices are symmetric and traceless. So if I take a delta AB, get 0. So you can do the counting for the degrees of freedom. So graviton does not have 2 degrees of freedom or D degrees of freedom. It's proportional to D squared because of the 2 indices, which you can work out if you want. Okay, so I have a photon over here which has polarization epsilon A, and it has momentum Q. And this is an on-shell momentum. Everything is on, all the external states are of course on shell. I'm considering an S matrix. And now I'm interested in understanding the structure of this S matrix in the limit where Q goes to 0. So remember, I'm working with 1 pi effective vertices and everything, so I only need to consider tree level diagrams. So as will turn out, there's only 2 types of tree level diagrams that we need to consider, and one of them will contribute and the other one won't. So let's start with the one that will contribute. So consider the following type of diagram where I have one external particle which couples to the photon, Q epsilon. Now just momentum conservation tells me that, so I want to make everything outgoing. So this one, if this one has momentum pk plus q, this has momentum pk, and this q goes out. And of course I'm assuming that pk squared is minus mk squared and q squared is 0. Okay, so what does this diagram evaluate to? What does such a diagram evaluate to? So it's very clear. So let's see. I get one factor from the wave function of the photon, which is coming from the polarization, which is E times epsilon A. E is the electric charge of the electron, or the fundamental electric charge. And I'm choosing a funny normalization. This is just a convention, which maybe QFT people don't like, but I'm choosing a convention in which the action is 1 over 4 E squared. The E is down here. So that means that factor of E down here will show up in the polarization, but it does not show up in this coupling here. Because the coupling, if I put the E down here, then the coupling becomes E mu, A mu, J mu, with no E out there. So the vertex does not have a factor of E, but the wave function has a factor of E. So of course it ends up working out either way. This is just a convention. So Q. So that's coming from this guy. Then what else? We have this vertex. The vertex factor is minus I gamma mu pk plus q pk. What was the convention I used there? I plus I gamma mu. Then I have this propagator. The propagator is minus I delta p times p squared. No, it's not p. Pk plus q, and then this is pk plus q squared. And then I have the rest of this amplitude here, which now is an off-shell amplitude, because one of these momentum is off-shell. So it's not the original on-shell amplitude, but it's some off-shell generalization of that, where all the other momenta are on-shell. So all the other momentum P1 stay the same, but the kth momentum is now k pk plus q, which is off-shell. Okay. Everyone agrees with this? Okay, now let's just take the q goes to 0 limit. So this stays the same, E epsilon mu A q. Gamma mu, now I'm taking the q goes to 0 limit. So that's exactly this limit that's showing up here. So in that limit, this factor is I times 2 times pk mu times qk, the charge of that particle. And then I need to take q to 0. But pk is on shell, remember. So when I take q to 0, that means I'm taking the momentum argument on shell and I just get 1. So this numerator just becomes 1. So I get a minus I. And then in the denominator, when I expand this out, I get a term which is pk squared plus mk squared, that's 0, always. Then I get a term that's, let me write it out. I'm going to get a term that's q squared plus 2 pk dot q minus I epsilon. But remember, I'm interested in the limit q goes to, oh sorry, well we don't need to, q squared is just 0 on shell, so I don't need to. I was going to say this is subleading, but it's on shell, so it's 0 identically. Okay, so this is the full thing, so let me just cancel out a whole bunch of factors and I'll get E qk pk dot epsilon A over pk dot q. Okay. What we note is that this is a pole in Q. There's a 1 over Q factor. So in the soft limit, the amplitude blows up. That's the first thing we learn. But it blows up as a pole, as a simple pole, 1 over Q. This is often referred to as a Weinberg pole. Okay, and all the other factors are just basically derived. And this is completely true because we're working with one PI diagram. So it's a completely, for all loop orders, derivation of this thing. Okay, of course this can happen for any k, so I just need to sum over all possible k. There's another possible diagram. So let's just remind ourselves where this 1 over q factor was coming from. There is no divergence in the q goes to 0 limit of this factor here or of the numerator of the propagator. So this entire pole was coming from the denominator. And it was coming because of the fact that the denominator is going on shell in the q goes to 0 limit. That's where this pole is coming from. So the only other diagram that we may have to worry about is where the photon does not couple to an external particle, but it couples to some internal line in the Feynman diagram. So I have some Feynman diagram here, then I have this vertex, photon, and some other thing is going on over there. And these could be connected in however way, whatever you want. Something like this. But now, these momenta that's sitting in over here, even in the limit where q goes to 0, this L will never be on shell. Because by momentum conservation, L is equal to sum of these momenta, and P1 plus P2 squared is not equal to 0, even if P1 squared and P2 squared are separately equal to 0. So these sort of diagrams in the small q limit will be finite. They will not give us the order 1 over q contribution. So they will not contribute to the 1 over q pole that we're after. So they don't contribute. So we can put this all together and simply write out the soft theorem exactly now, and the soft theorem is the following statement. So we take an n plus 1 point amplitude, which is given by a q and an epsilon. Oh, by the way, I did forget a whole factor there. I forgot about this a factor. Now when I take q to 0, this becomes an on-shell amplitude. So this goes back to becoming an S matrix. In this line, this was not an S matrix, it's an off-shell amplitude. But now that when I take the q goes to 0 limit, now this goes back to becoming a proper on-shell amplitude. S matrix, in other words. So in the limit when I take q to 0, and also this is true in any dimensions. I never said anything about dimensions over here. Sum over k, qk, You see, this doesn't depend on any details of the theory. This could have been any quantum field theory. The particles could have been any particles, scalars, fermions, whatever. You could have higher dimensional couplings. You could have f's to the 5 terms. You can have whatever, any sort of couplings that you can possibly think of. And no matter what, this will always be the soft limit. Yes?
The diagonal ratio doesn't contribute to the leading one, the second one contributes to the subleading one?
Yes, it does. But that's also associated to symmetry, so perhaps a bit more surprisingly, it's also universal. Yeah, but that's not as obvious as the leading one is.
Why can you consider only this one pi vertex, not the higher one?
Maybe that's a very good question. A very good question. I did. Sorry, yeah, you're right. You're right. There's a third type of diagram that we could have considered, in which even suppose I have this external particle coupling, but now I have the photon, but I have an extra vertex. I have a 4-point vertex. That's a very, very good point, and I should have made this point. What's going to happen in this case? So when I take the limit q goes to 0, this is the internal momentum. It's not going to go on shell, because momentum conservation still tells us that this is equal to the sum of these two momenta. So it's never going to go on shell. So it's not going to contribute to the pole. But it is going to contribute to the subleading soft theorem. So it's also something we have to consider. So very good point. We do in principle have to consider all these endpoint effective vertices as well. But for the same reason, the internal propagator never goes on shell when I have more than 3 vertices. And so they can never contribute.
And you're considering only one external photon. So
Right now I'm considering one external photon. And as an exercise to you guys, I have a bunch of exercises now. Here are every one of them uses exactly this method. In fact, the only thing, maybe I can just tell you, the only information you need is, let's go in here. So I'll write it in here. In the case of gravity, in the soft limit, this is always true, no matter which theory I'm sitting in, whether it's gravity or not. In the case, if this is a graviton, then I have a mu nu index, and then this propagator goes to 2 p nu in this. So now the charge that couples to gravity is the energy momentum itself. So in other words, you just have to replace q with p mu, and you end up with the right propagator in the soft limit. And you can also do this for Yang-Mills, in which case this is 2 times Ta. Now in the case of Yang-Mills, I have a mu index and I have an A index. Then it's 2 times Ta times p mu. Ta is the generator in the representation of the gauge group in which that particle transforms. So that's it. These are the only things you need. Just how this 3-point vertex changes. And then you can do the following exercises, which I'll suggest to you. Where did here are some exercises for you guys. So what happens for m greater than 1 soft photons? Similarly, m greater than, well, we've already done m equal to 1 over there. So similarly you can do m greater than 1 soft gravitons. Similarly, do m equal to 1 soft gluon. And in this case, I'll have a question for you. Why is m greater than 1 hard? Anything else? One way to see that m greater than 1 is equal to hard is to look at double soft limits. So you take the following, do 4 over here. So if I now consider the following limit q1 goes to 0, of an n plus 2 point amplitude with 2 gluons in them. Of course, this will be labeled by A and B. So I take the limit q2 first, then q1, do it the reverse order, then subtract. So that's the commutator of soft limits. Show that this is not equal to 0. In other words, in the case of gluons, but not gravitons and photons, multiple soft limits care which order I take the particles to be soft in, which is exactly why, well, I sort of answered it for you, which is why m greater than 1 is hard. Okay, you can think about these as exercises.
So can you raise the other board?
Yeah. All you will need for 1, 2, and 3 is just those that information there. This is also very simple actually, because this is simply consecutive soft limit. So you just have to you apply the soft theorem once, you get a soft factor plus a lower point amplitude, and then on that lower point amplitude you apply the soft theorem one more time, so you get a product of two soft factors. And then when you take the reverse, you'll simply get a difference of those products. So then the question simply is that, does the soft factor commute? In this case, the soft factor is a number. So you just multiply two numbers and it will commute. Makes perfect sense. In this case, because of the fact that in the Yang-Mills 3-point coupling, the TA is appearing, which is a matrix. The soft factor will not be a number, it's a matrix. And so the commutator of soft factors will be related to the commutator of TAs, but that's the algebra. So this is another way to say this is that in fact the commutator of soft limits probes the algebra of the gauge group. Yes?
Experimentally, if we're taking two gluons to the soft limit, which of these orders will we measure?
No, there's no such thing. You have to take different orders. You have to specify which order. Experimentally, you can't, you have to specify it anyway. Even in all these other ones, you have to specify it. It just so happens that in all these other ones, it doesn't matter. Yeah. And here's also another fantastic feature. Now specialized to d equal to 4. Another exercise maybe. You don't have to do all of them. I'm just, if you're interested, many of them may not play any role in our lecture, so it's up to you honestly. Especially in d equal to 4, remember then I told you that the gluons are labeled by mu and a and the helicity. So this factor, whatever you have over here, in the case when d is equal to 4, in the case where the helicities of the two gluons that I'm taking to be soft are plus plus and minus minus, is 0. So actually the soft limits do commute when the helicities are the same. But when it's plus minus, then they don't commute. This is sort of another indication of the idea that Atul was saying. It's very hard to sort of describe a theory in which both helicities are present at the same time. If you just have one helicity, then you can deal with this entire soft sector very nicely, because all the soft limits commute and everything exponentiates. As you will see, if you try and just think a little bit about what happens when m is greater than 1, you will see that it's not really that hard. It's because everything commutes. The product, when I have n soft factors, n soft photons, is just that soft factor to the power n. That's it, because everything just factorizes nicely. And that also happens here in the 4-dimensional case if the helicities are the same. Now I can do multiple pluses. But the moment I start including an extra helicity, the entire soft sector goes haywire. This makes it super hard. It's an open problem, so I won't have much to say about it.
This is another version of the same googly.
Yeah.
Are there soft theorems for mixed symmetry tensors in higher dimensions?
Yes. In fact, well, we know that there's soft theorems for gravitons, there's soft theorems for the dilaton and the Calvert-Mont field. And in general, I think Anna has some work in which she has generalized, but she's done it in 4 dimensions, but I think that story can be generalized where you have soft theorems for arbitrary higher spin gauge fields as well. I think that can be generalized to greater than 4 dimensions also. But the dilaton and Calvert-Mont field come to mind particularly because they are the soft theorems that are relevant in string theory, which show up all the time.
Maybe I missed this. Sorry. Did you say that in higher dimensions this problem doesn't exist?
In higher dimensions it absolutely exists as well, but I think there might be limits in which you can make like 2 of them to be 0. In higher dimensions, there's a nice, amazing tensor structure which shows up, which I will tease over here. No, maybe I won't do it now. But I'll just tell you that there's this thing in CFTs called a conformally covariant tensor, IAB. Oh, I've now realized I made a notational error. A index over here is not the 1 to D. This is the, let me call it IJ. This is the Lie algebra index. That's not the AB indices here. But in fact, you can check. I haven't explained to you exactly how this mapping works, but roughly this shows up as Fijk, which is expected. The structure constants show up because we know in the abelian case it has to go to 0. Sum over k, and then there's a Tk, k that goes over here with this lower point amplitude An, and then the factor that sits in here is, in fact, remember now these gluons have polarizations, epsilon A and epsilon B in higher dimensions. So there are these AB indices over here, and they show up as these AB indices over here. And this is just delta AB minus 2. This is a very important tensor in CFTs that plays a role in shadow transforms.
This occurs all over the place when you compute Witten diagrams.
Yes, because Witten diagrams essentially are also doing shadow transforms all over the place. Yeah, this is why I sort of didn't want to fully introduce it at this point, but roughly speaking, I'm going to talk about this in sort of a later lecture where I parameterize my Q momenta. Remember, the momentum Q can be parameterized in terms of an energy E and a point on the sphere. And the point on the sphere I'm going to label in terms of stereographic coordinates. So there's this X label over here. So each of these momenta Q1 and Q2 are labeled in terms of E1 x1 and E2 x2. And I'm taking the soft limits. So I'm taking the limit where E1 and E2 goes to 0. So those variables disappear. So the only thing that's left is x1 and x2. So the right hand side depends on x1 and x2, and that's what's showing up here, x1, 2. And this tensor structure here is exactly this conformally covariant tensor in a CFT. This will show up again when we talk about shadow transforms later in these lectures.
So this is for arbitrary pair helicity.
Arbitrary helicity. This also, by the way, this formula is also true in 2 dimensions. So you can actually show that in 2 dimensions, when I have this IZZ is 0, IZ bar is 0, which is why same helicities commute, but IZZ bar is roughly like Z over Z bar. So they don't commute. But they don't commute in a very interesting way. It's just a phase. So I think it can still be controlled. The way they don't commute can still be controlled in some way, and we can maybe say something interesting about it. But this is an open problem. But I haven't introduced any of these things for you yet. An exercise would simply be to write this equality not in terms of IAB, which I haven't really explained in detail for you, but in terms of momentas and epsilons. And I do have lecture notes which I've typed up, which I'll share with you guys, and the exact formula that you need to derive I have written out there. So you can do that. Okay, any questions before I move on to the last topic of the lecture? Yes.
What is the algebra index?
I1 to n. This is the generator in the for the ith particle. And K is the Lie algebra index. So that's whatever Lie algebra the gauge group is.
For this leading soft theorem, does this consecutive limit matches with the simultaneous limit?
No, not for gluons.
But it matches with photon versus?
Yes.
But for subleading it doesn't match.
Because it doesn't commute. Same reason. Every time the soft theorems stop commuting, you have a problem. And the reason this subleading doesn't commute is that, as we showed here, in the leading case, this is a number, so that commutes. In the gluon case, it was a matrix. That's why it did not commute. In the subleading case, for photons, it's a derivative operator, which doesn't commute. In the case of gluons, it's a derivative it's a matrix derivative operator, so it doesn't commute in even more complicated ways.
Can one trace it to the fact that the gluon have this strong interactions?
No, it has nothing to do with confinement. It has to do with the fact that the soft sector is a non-abelian gauge theory. Now you might have asked, well, if that's the case, then why did it not show up in gravity? Gravity is clearly a highly non-abelian theory. It's very nonlinear. But the soft sector, remember, what is the charge corresponding to gravity? It's the energy. So when energy is small, it's abelian. So the low energy sector of gravity is completely abelian, which is why you see that these soft factors completely exponentiate in the case of gravity. But they don't do that in non-abelian gauge theories.
And what happens in this multi-graviton theories?
What? I don't know. What is the multi-graviton theory?
Some people that do like massive gravities that model with two gravitons, geometric models.
I don't know. But the soft theorems will have to hold because the soft theorems don't care which theory I'm sitting in. I don't know about what happens with multiple soft limits though. If it's massive, then there's no soft limit. I also agree.
Yeah, if you have multiple one, there's only one which is massive.
If there is a massless graviton, then the soft theorem holds. I don't know anything beyond that about it. Thank you. All right, I have like 15 minutes left. Let me talk now about IR divergences. So when I first learned in my first course on QFT, when we reached this stage, when we started talking about IR divergences, my professor Matthew Schwartz basically said this is the most important calculation that you'll ever do in QFT, and it really is. It's very difficult. It's very lengthy, and obviously for that reason, I'm not going to be able to present all of that. Forget about 15 minutes, let alone maybe in an hour even. What I'll do is I hope you have already seen this calculation on IR divergences, but I want to highlight some features, maybe not relevant to the lecture itself, but some features that many books don't really talk much about or don't highlight themselves. Even Weinberg misses out some of them, some of these details, which I'll highlight them for you, and I'll just tell you essentially what the final answer is. In my lecture notes in the appendix, I have presented all the details of everything that I'm not going to say about today. So you can go through that if you're interested. Okay. So what is an IR divergence? So there's something that I sort of lied to you a little bit about. Those soft limits that I wrote to you over there, when limit q goes to 0, gives you 2q p mu, that comes from renormalization conditions from UV divergences. However, in theories, in massless theories, there are often also infrared divergences, which you cannot get rid of using counter terms. They're actually physical. They're telling us something important and physical about the theory. And when you have IR divergences, those limits are often not true. They're true to some extent. They have to be modified slightly. There is still some formula, but they have to sometimes be modified. So let me now tell you what these infrared divergences are, where they are coming from, and how they affect these sort of things, and consequently how they affect the soft theorems themselves. So before talking about the soft theorems, let me just talk about IR divergences in just a general amplitude. Everything is hard. There's nothing soft. Okay, so an amplitude that I'm going to consider is something like this, some general amplitude. And let me consider now the following contribution. Okay, so let me explain what I'm doing here. The goal is to understand the contribution of soft photons, virtual soft photons. Here in the soft theorem, we were talking about real soft photons because they were external photons and they were on shell. But when I have a gauge field in the theory, I have to do loop integrals, and in one of those loop integrals, I need to integrate over small momenta as well. These contributions are called virtual soft photons. They're not on shell. That's what I'd like to do. So what I'm going to do is I'm going to introduce two cutoffs, a cutoff lambda and a cutoff mu. And I'm going to define soft photons as the set of all momentum which lies between mu and lambda. And lambda is not the UV cutoff. I'm assuming UV divergences have been regularized, we've added counter terms, all of that has been dealt with. It's done. Now I'm going to talk about the contribution of soft photons. So soft photons are any photons which have energies in this, I'm just introducing by hand. Mu is going to be my IR regulator. It's going to be the thing that regulates my IR divergences. Eventually I'm going to take mu to 0, and we'll see that you can do that in D greater than 4, you cannot do that in D equal to 4. And we'll have to resolve this issue, and why that's happening, we'll have to fix that. Lambda is just some arbitrary cutoff that I've put in by hand. It sort of delineates my definition between hard and soft. I can choose that to be whatever I want. Sometimes it's imposed to us by an experiment. If my experiment has a low energy cutoff that it cannot do measurements below a particular energy level, then that lambda is fixed by the experiment that you're trying to perform. But if you have no such experiment, if I'm just looking at it theoretically, it's just something I've introduced by hand. So I'm assuming that all the contributions from hard photons, that is for energies greater than lambda, have been taken care of. Those UV divergences have been completely regularized. We have one pi effective action, and which is all counter terms have been taken care of. And now I'm just going to focus on the contribution of these parts, which is the leftover piece in the theory. Okay, so let's start. The essential idea is going to be the same as the one that showed up in the soft photon theorem part. So let's start with the following contribution first. So I have two external particles. So pk prime, and let's say I have a soft gluon that's a soft photon that's going through these particles here. So consider this diagram first. There are many others. Let's start with this. So this is pk plus q, pk minus q, q. Okay, and remember q is very small. So it's taking this formula. But because q is small, I can use those properties over there. Okay, except the problem now is that the q that is showing up there, the capital Q that is showing up there, is the q that is hard renormalized. It's the renormalized charge that you get when I include contributions from hard photons. I have not yet said how this charge is renormalized when I include the contribution from soft photons. So in fact, the first step before even trying to compute these S matrices is to ask the question, how do soft photons renormalize Q, how do they renormalize M, and how do they renormalize psi, the field? Why does that matter? This matters because then the renormalization of the charge will affect this formula. The renormalization of the mass will affect the exact limit that I'm taking, and then the renormalization of the field will affect whether this is 1 or not. And we need all of these pieces of information to completely understand the structure of the amplitude. This is the part that you won't see in Weinberg. He doesn't go into details, but I'm just going to tell you this. I can't go through. I don't have, even within 6 hours, it's very difficult to do. But again, it's in the appendix. Here's the fact. Soft photons do not renormalize Q, they do not renormalize M, but they renormalize the fields. Okay?
And
Yeah.
It's not through the presence of counter terms?
Hmm?
It's not by adding counter terms at this distance?
No, I'm not adding any counter terms. You can just show that if you try to compute the renormalized charge, that it stays exactly the same as before. In other words, how would I compute this? So what I need to do is how do I define charge? Remember, I define charge by, I need to compute this Feynman diagram. And this is the full Feynman diagram, the full contribution, including soft and hard. So what I need to do is I need to break this up into soft contributions and hard contributions. So for example, I can have diagrams that look like something like this, and you might think I can have diagrams that look like, let's say something like this, the 4-point vertices as well. Why not? As I said, I'm doing something in a completely general theory. So in principle, you can have such diagrams. But again, because of that fact, that we only care about contributions when the things go on shell. That's the leading divergence, is when internal propagators go on shell. These diagrams will never contribute to that leading limit. Only these diagrams contribute. And now because I'm in an abelian theory, they all exponentiate. So this diagram is basically just this one thing squared. And then there's some symmetry factor, so on and so forth. So this entire thing is just the exponential of this diagram. But you'll see that this is exactly the diagram that you'll also get from the field renormalization. So this completely cancels the field renormalization and the charge remains unrenormalized. The mass also remains unrenormalized for similar reasons, but the field does get renormalized.
That will not be true for the non-abelian case.
A non-abelian, because this exponentiation doesn't work right there. And we don't know how this works in general. This is a big open problem. All right, I don't have much time. So anyway, so again, the details are in the appendix. You can take a look at it if you want. The main thing I wanted to point out is that the field does get renormalized, and it gets renormalized in a really very nice way. And so the only thing that gets changed in these things is this limit. This is no longer 1, it's some z that we can work out. And you can check explicitly what this is. Okay, let me keep that in mind and keep going on. Actually, we call this z to the, what is it, minus half. You know, that's the convention we use. Anyway, but charge mass, no renormalization. Field renormalization, yes. Okay, so let's quickly evaluate this diagram in the very soft limit. So now this q is an internal line. So I have to do a loop integral. So I have an integral over d dq. And the integral is only from mu to lambda, remember, in this region, because I'm only interested in soft contributions. Okay, this is very easy. Because q is small, I can essentially use the soft theorem. And I know these limits. I know I've already assumed that these limits are all fine except for this factor of z. So the only thing that I have to check is that I'm going to get an extra factor of z from this propagator and an extra factor of z from that propagator. And then whatever you get from this propagator. So when you do all of that, the full thing you get is at the end of the day qk prime. Sorry, I should say this again. This is not the right way to. The idea is that when you do LSE theorem, this limit should always be 1. That's how we should think about this. This limit should be 1, otherwise the LSE theorem cannot be applied correctly. So what I meant to say is that the hard delta goes to z to the minus 1/2. So I need to change the renormalization of my fields. I need to redefine my fields goes to z to the minus 1/2 psi in order to cancel out this factor. So what I should be saying is that this limit is still equal to 1, but now my wave functions, each of these, pick up extra factors of zk and zk prime. Yeah, that's the way to think about this. So I get pk dot pk prime over here. Now I get one factor from this propagator going on shell. So that's pk dot q. One factor from this guy going on shell, pk prime dot q. And then one factor from this propagator, q squared. And I've not written factors of I epsilon for simplicity, but they're very important in this entire calculation. Okay, so that's what this diagram looks like. And there's a factor of I, e squared coming from this propagator over here. And that comes because of my funny normalization of my kinetic term. All right, so, and again, for the same reason in the soft theorem, you can convince yourself that these are the only types of diagram that contribute to the leading divergence. So what do? The full answer, therefore, and I forgot a factor of this amplitude also, this an. The hard amplitude, this is the hard amplitude. So the full answer now is the following: an everything, so including the soft factor, which depends just on this this IR cutoff mu, is equal to what? So what is it that I have to do? The first step is that I need to sum over all possible k and k prime, right? Now here's the cool thing that happens. This is why it's really nice. In principle, you're supposed to sum only over k not equal to k prime, because this is going over different particles. So what happens to the term when k is equal to k prime? That's coming from the field renormalization. It turns out to give us exactly the same factor, because where is the field? What are the field renormalization diagrams? Those diagrams are something like this is what I have to compute, which is essentially this diagram, but when k is equal to k prime. There is a crucial I epsilon distinction we have to make, but I'm not going to bother over here. But the essential idea is that at the end of the day, when I sum over all possible k and k prime, it's just going to be, I also have to include the k equal to k prime, which is coming from the field renormalization factors. And then I need to exponentiate, because here I only considered this one diagram, but I could have also considered this diagram with two soft photons, and then 3 soft photons, 4 soft photons, and they all exponentiate symmetry factors 1 over 2 factorial. So they all at the end of the day become an exponent. And the full answer is e to the minus gamma a n hard, where gamma is this exact, I'm calling it a, sorry. A is I that's the full thing. Okay, this is not a bit, it's a very messy calculation, but I honestly think, I mean, if anyone who takes at least one course in QFT should at some point do this at the end of their thing, they should really go through this calculation in detail. It involves lots of QFT techniques, essentially all of them you need to understand to do this calculation. It's really a very good test of whether you've understood QFT. So I would suggest going through it in any detail. Okay, so let me now summarize the result. In a later lecture, you see how much effort we had to go through to derive all of this. Later in these lecture series, I'm going to derive this entire thing using symmetries. Just using symmetries and not doing a single calculation. I'm going to use just some effective field theory, and I'm going to do a Gaussian path integral in a quadratic theory, and I'll be able to derive this entire factor using just symmetries. It's one of the few things that you can see why the symmetries are really, really powerful. And I won't have to go through all of this nonsense of renormalization and stuff. So that's one thing I'll talk about. Another thing to note is that this A, let's look at how this falls off in general. So you can just sort of read off the powers of Q. So in general dimension, this entire thing goes like ddq, and then in the numerator I have a factor of q squared, a factor of q, and a factor of q. So I'm just looking at dimensional analysis. So dimensionally speaking, this goes like 1 over q to the 4. So in greater than 4 dimensions, this is like q to the d minus 4 when I perform the integral. And this is totally finite in the q goes to 0 limit when d is greater than 4. So you see that when d is greater than 4, this factor is totally finite. It's usually non-zero because I'm not taking lambda to 0. Lambda is fixed by my detector, whatever it is. But it's something that's completely finite, no issues. So we shouldn't really be calling this an IR divergence, at least in greater than 4 dimensions. But in 4 dimensions, this is a log of q. So when this is a log of q, then when I take q to 0, I get a divergence. And you'll see that in that case, this entire thing ends up being something that looks like lambda to the mu to the power minus c a n, where c is exactly what you get after you evaluate this integral, which I will do later in the lecture. The only important thing to note is that c is positive, which means that when I take mu to 0, this goes to 0. this is the statement. So therefore, the statement is in 4 dimensions, an S matrix in the presence of massless particles, strictly speaking, is 0. There are no non-trivial S matrices. Everything is 0 because if I include all the contributions of the soft photons, the amplitude exactly vanishes. This is what's referred to as the infrared divergence problem. It's called divergence because at this is infinite, but the exponent of that is like e to the minus infinity. So each individual diagram is infinity, but the sum is 0. So we'll see how to resolve this, because this is clearly not really true. Obviously, we measure S matrices in LHC all the time, so there has to be some resolution. So we'll come to that.
Why do we not conclude that there is an higher cutoff?
We do that. That's one of the ways to resolve it. That's how most particle physicists like to resolve it. You put in the IR cutoff and you only talk about inclusive cross sections, and then everything is IR finite. Once you include the inclusive cross sections, then you can see that you can take mu goes to 0, and that's perfectly fine. You can do that. As theorists, we don't want to do that because I'd like to have a IR finite S matrix, because otherwise I want to test unitarity of the theory and various properties that's hidden in the S matrix. So as a theorist, I would prefer, I mean, if it doesn't work out, then I'll have to deal with it, but I would of course prefer to be able to write down an S matrix itself that is IR finite and not talk directly about cross sections and decay rates and that sort of stuff, which is basically how particle physicists like to deal with it. What I'd like to do is like to find a new S matrix, quote unquote the correct S matrix, for reasons that I will explain, which is completely IR finite. And this was already done in the 1970s, so it's not going to be something new, but I'm going to redo that entire calculation using only symmetries. They had to guess it because they had to look at all these structures to find what the right answer is, and it was really messy. It wasn't clear why what they're doing is correct and there's nothing else you can do. Whereas I'm going to do everything using just symmetries, and you'll see that it completely fixes everything. Okay, I'll stop here. Sorry for going over. Thank you.